Welcome to Dr. Jed's ongoing calculus video series. Today's lesson is section 3.9 from Rogowski, exponential and logarithmic derivatives. We've seen some of these before, but they put them all together and added some more. So the first thing we're going to do is do some formulas, find out the derivatives for exponential and logarithmic forms. I'm going to do a derivation of the natural log of x, its derivative, using the inverse function theorem from the previous section. Do a quick example. Then, because there is so much in this section, we're going to move on to hyperbolic derivative formulas. Remember them? If not, they'll be on the board too. And then do some examples to round out today's lesson. First off, the formulas. We know the derivative of e to the x is e to the x. We also learned the derivative of b to the x is b to the x times the natural log of b. Although, we may not have learned it until this section, depending on which class you're in. So, e to the g to the x, we learned that one, and as an extension, b to the g to the x's derivative is b to the g to the x times the natural log of b times, remember this piece is always important when you're doing a chain rule, times the derivative of g of x. The ones that are really new now, the derivative of natural log of x is 1 over x. It's actually kind of surprising. Natural log of x is a logarithmic function. Its derivative is rational. It's x to the minus 1. It's actually very strange. And if you put a g of x in there instead of an x, it's the same kind of thing, except that in this case, because we've got a fraction, we can combine them into one kind of common fraction here. And likewise, log base b of x, the derivative is 1 over x natural log of b. If that's a g of x, this is going to be g of x here, and we'll have a g prime of x on the top. Now, let's do a quick derivation of this one right here, because this one's probably the most interesting one. It's using the inverse function theorem. So this is the inverse of a function. So our inverse function, it's the inverse of e to the x. The derivative is 1 over the derivative at the inverse function. Now if you recall, the derivative of this, again, is e to the x. So this would be 1 over e to the natural log of x. The property of inverse functions, e to the natural log of x, is 1 over x. Now sometimes you will see this as 1 over the absolute value of x. That's true too. But since we're talking about the natural log of x, not the natural log of the absolute value of x, this makes no sense when x is negative. So that's not really necessary. If we were talking about the derivative of the natural log of x, then it would be necessary. But let's do a quick example. The derivative of x cubed natural log of x. This is a product rule. So the derivative of a product is the derivative of the first one times the second plus the derivative of the second times the first. Now that is the derivative, but it's important to remember, this is not simplified. It's not too terrible, but this right here could be fixed. We have 1 over x, we've got an x cubed multiplied on. Well, you know, that's x cubed over x. That's an x squared, basically. And this is x squared, so we can factor an x squared out of everything and get x squared times the quantity 3 ln x plus 1. Alternatively, if you want to do the same thing but you just don't factor, we have 3x squared ln x plus x squared. One of the bottom two is going to be simplified, depending on how you think these things through. If you like this bottom one better, if you think it's easier to understand, that's simplified. I think most people will prefer this middle one. I think it's a little bit easier. Not a lot, it's still got the natural log, they all have it, but that's probably the simplest form. Now, as I said, there's more to this section. Remember, there are hyperbolic trigonometry functions. We defined the inverse sine of x, the hyperbolic sine of x. All these inverses and things swimming around, you can get confused. The hyperbolic sine of x is e to the x minus e to the minus x over 2. And the hyperbolic cosine of x, or cosh, is e to the x plus e to the minus x over 2. Notice there's a minus here, there's a plus here. The hyperbolic tangent, we just get it. This is the hyperbolic sine of x over the hyperbolic cosine of x. The hyperbolic secant of x is going to be 1 over the hyperbolic cosine of x, and so forth. Now, those are the functions. The derivatives are here. The derivative of the sinh of x is the cosh of x. The derivative of the cosh of x is the sinh of x. The derivative of the tangent of x is the sech of x. It's hard to say these, but notice, look at these for a second. You should see a pattern here, something you've seen before. These are very much like the non-hyperbolic derivatives, except that the non-hyperbolics have a minus here, don't have a minus here. Do you remember if they have minuses here? Well, they're very much the same, aren't they? That's why they're called these functions. It's actually kind of surprising when you think about it. These are defined using e to the x's, not trigonometry. And yet their derivatives are almost the same, almost exactly the same, except for a few minus signs. The inverses, to take a look at them. I'm not going to derive them, but you do them with the inverse function theorem. The inverse of the hyperbolic sine is 1 over the square root of x squared plus 1. That's a little different than the previous one. The previous one, without the hyperbolics, was 1 minus x squared in here. If you think about that, it's just a minus sign different. Likewise here, there's kind of just a minus sign different, but on both pieces. Again, a minus sign different, and so on. Notice there's no absolute value here because the inverse hyperbolic secant can't take on negative x's. It's not possible. Why? Because look back here. If it's 1 over this is the hyperbolic secant, this is never negative. So its inverse is never going to be negative also. Now, they're messy formulas. They're not something you just go, okay, I got them. You spend a little bit of time to remember them, and maybe right before a test or some other thing you have to really know them for, you just memorize them. These are pretty good. You should know these ones, especially since they're so similar to the regular trigonometry ones. The top two, maybe you use them enough to eventually get used to them, but even so, these are messy. They're just more formulas. But there's good news. These are the last formulas. The last formulas in the entire chapter. The rest of the chapter is other stuff. But there's no more formulas. So we're done with that. Let's do an application of them. Hopefully that'll help. Show that y equals cosh of 2x is a solution of this differential equation. Well, to show that, we just need to find what this is. This is the second derivative. So let's take the derivative of that. It's the chain rule. The derivative of the cosh of something is going to be the sinh of it. But then, since that's not x, it's a chain rule, it's times the derivative of that. So we're going to get the sinh of 2x times 2. Now, be careful when you do this. Make sure you have parentheses the right places. It will look awkward otherwise. The derivative of that, the derivative of the sinh is the cosh. And it's a chain rule again. So we have the cosh of 2x times the derivative of the inside, and then still times that one. Now, if that's the second derivative, it's just 4 times this, right? So look at that. It works. It's not a very hard differential equation. It's a useful one, but it's not very hard. But hopefully it shows you that you can use derivatives. Let's close with one more example. Just finding the derivative of this function. No fancy differential equation, no tangent lines, just a derivative. So the derivative of this, think back to what the derivative formulas were before. The derivative of the log base b of something is going to be 1 over x times the natural log of that b times the, derivative of this. But I made a mistake already because this is a chain rule. This is not an x. So rather than erase it, I will just write over it. I don't put the x there. The x is if this is x, and it's not. This is that. If you get too rushed, you're going to make mistakes. And when we multiply on the end again, since it's a chain rule, this is not this times this, is this of that. So the chain rule says also times the derivative of this. Now you could put that on top. I'm not sure if it makes much difference, or you can leave it that way. Until next time, this is Dr. Jeb.